Hello, hello, whoa, hello, Pre-Calc 11. It's another overcast day. Hope you're having a good one. We're doing more trig. Here we go. So, today we're looking at trig ratios and angles in standard position. We've already talked about angles in standard position and reference angles. This is the page number. It's also on the assignment. So let's roll through this. All right, here we go. So here's the theory behind what's happening in today's lesson. So let's pretend that someone had given you an angle in standard position that, thinking of it as the angle that we talked about last time, like this, starting with the initial arm and it ended in quadrant 2 as an example. If we were to then take this situation and think of a point that was on this initial arm, and as the point was spinning around the arm, it would trace out a circle if it went all the way around. And what we're trying to do now is we're trying to get trig back into the mix of our angles. So, and we're going to try to get SOHCAHTOA back in. And in order to get SOHCAHTOA, you need a right angle triangle. So if you consider this point here that ended on the terminal arm, let's call that some point xy. They'll give you numbers for specific examples, but this is the general. If I was to make a right angle triangle, the trouble is, here's the angle we're speaking of. The right angle triangle, the only place we can actually develop that is one place is right here. We're going to drop this to the x-axis. And this angle in here, which we had talked about before, that's going to be the reference angle. So that's why the reference angle is so important, because no matter what quadrant you're in, you'll always have a reference angle, and you'll be able to drop the point to the x-axis and get a right angled triangle. More importantly, the length of this side of this triangle is the x-coordinate of that point, because that's how you draw the point. You go x over, and the y value would be your up or down. In this case, the y is up. That would be y. And because this is a circle, this hypotenuse of the right angled triangle is, they call it r for radius. Okay, so r is the radius. And there's 4 relationships that come out of here that you know from grade 10 trig. First is Pythagoras with that right angled triangle. X squared plus y squared equals r squared. A squared plus b squared equals c squared. So that's one relationship that you will always know. The other one is SOHCAHTOA. You will know sine of the angle, cos of the angle, and tan of the angle. Now, even though we're talking about this angle here, we're using the reference angle in our mind, so to speak. Well, I can put that there if you want, to actually go from there. So here's where we have. So sine of the angle is opposite, which is y over the hypotenuse r. Y over r. Cosine is adjacent, x over hypotenuse r, and tangent is opposite over adjacent, y over x. So those 4 things will always be true. I personally use the picture to remember those. Some people just memorize that forever. They just know that if you're dealing with a point on the terminal arm of a standard position angle, these 4 things come out. Okay, on top of that, something else that comes out that is interesting, because we're dealing with angles that are bigger than 90 and bigger than 180 even, they can go round and around and around in any quadrant. If you think about it for a minute, and here's what the cast rule is, and it's kind of a neat rule. You don't see the application of it yet until we get into the examples or to the solving. But what will happen if you have an angle that ends in quadrant 1? Okay, so first of all, if it's in quadrant 1, the x value is positive for that point, and the y value is positive. So because the x and y are positive, sine y over r, x over r, and the r will always be positive. Let's put it that way. So the y, the r, the x, and the r, the y, and the x are all positive. Sine, cos, and tan will always spit out positive ratios. So sine is positive, cos is positive, tan is positive. When it floats over to quadrant 2, like we were here, the x value is actually negative, the y value is positive, the radius is always positive. So now because x is negative, the cosine value, you have a negative divided by positive, you get negative. This will stay positive because y is already positive. And you have positive divided by negative, that's negative. So you end up with sine being positive, cos being negative, and tan being negative. So we're going to get to the rule in a minute. Right now it's just kind of weird facts. So as you move around, the ratios will change signs. They won't change their size, they'll change their signs. In quadrant 3, the x is negative because it's left, and the y is negative, the radius is positive. So if x and y are both negative, and radius is positive, that ends up being negative. This ends up being negative. This ends up being a negative divided by a negative, which ends up turning positive. So you end up with sine being negative, cos being negative, and tan being positive. And then in the last quadrant, you end up with x being positive again, y is below, so it's negative, and radius is positive. So sine ends up being negative, cos ends up being positive, and tan ends up being negative. Now that's a lot of things to kind of memorize. So you got 3 things here, 3 things there, 3 things there, 3 things there. That's 12 things. So what someone came up with is a little acronym. They call it the CAST rule because it makes a nice spelling. But technically, if you look here, in quadrant 1, all of them are positive. So they call that all, A. That's the A of the CAST. In quadrant 2, sine is positive, cos and tan are negative. So we're just going to memorize the positive. Sine is positive. By default, sine and cos are negative. Sorry, cosine and tan are negative. In quadrant 3, sine negative, cos negative, tan's positive. So tan's the only one that's positive. So far we're getting, there's the AC, there's the AST for the CAST part of it. In the last quadrant, cosine is the only one positive. So cos is positive. Now, they could have called it the AST rule, but they call it the CAST rule. I personally memorize it as, so the ASTC. I know it's corny, but it works. Lots of acronyms I've heard, like all students take calculus, all suckers take chemistry, all suckers take cocaine, whatever you want to make it up to be. Just remember it starts in quadrant 1, ASTC. So that's called the CAST rule. So if anyone ever talks about the CAST rule in math, that's what that little rule is. Now at the moment, this doesn't mean anything. It's just like, okay, these are just weird facts. Good for it, good for it. Let's see how we put this into play. All right, so here is an example. They've given me a point, -5,7 lies on the terminal arm. Just means that point is on the terminal arm of the graphic of the angle theta in standard position. So it's good to know its standard position is starting like we did our last lesson. It wants us to determine the values of sine, cos, and tan, and find the value of theta if theta is between 0 and 360. And that just means it's going to be in one of the 4 quadrants. So what I personally prefer, always a picture. So right away, even if I had no idea about any of that, I should know how to plot a point with my grade 7 skills. So I would plot that point. I'd be like -5,7, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 7. And I'd plot that point, boom. I don't even have to do it to scale. I'm just doing it quickly. And it says, so I could do that. That's done. That lies on the terminal arm. So the terminal arm must be there, meaning it must have started here, meaning then the actual angle that we're speaking of is that. So I even know right now the angle that I'm going to be finding in part B, it's going to be between 90 and 180. I just know that. Now the next thing I want to find is sine, cos, and tan. Well, that says, well, I need to use SOHCAHTOA. I need a right-angled triangle. How do I get a right-angled triangle? Well, I have to drop that point to the x-axis, always the x, because you want the reference angle here to help us out. And then what do I know? Okay, I know the length of this. This length is -5. I know that makes no physical sense, but remember we're dealing with abstract thoughts now. That triangle length is -5. This here is 7. And then from there, I just need to figure out what the radius is. And once I have the radius, I'll be able to figure out sine, cos, and tan. Either by the picture would tell me sine is opposite over hypotenuse. It's going to be, this is the y value, this is the x value, this is always going to be y over r, this is x over r, this is y over x. I just need r. Now how do I find r? My little buddy Pythagoras. So I know that x squared plus y squared equals r squared. I know that negative 5 squared plus 7 squared must equal r squared. 25 plus 49 equals r squared. So this gives me what? 74. So r must equal the square root of 74. Now just to avoid ugliness, I could change that to a decimal. I don't feel like it. I'm just going to leave it like that, and then I can look here and say, well, sine theta is going to be 7 over root 74. Cosine is going to be negative 5 over root 74. And tangent is going to be 7 over negative 5. And I could rationalize, like the last unit, I could multiply both top and bottom by root 74. So the back of the book might, depending on their mood, they might rationalize it. They might leave it like this. That's just a matter of choice. They don't have to. They're both right. This one's already rationalized. The only thing I might do is put the negative on top just so it looks prettier. Okay, so there's my part A done. Okay, that's all I want. Just the ratios. Part B, though, says, find the actual angle, please. And then at that point, I need to figure out the size of this reference angle, and then I can easily subtract it from 180 in the picture to find out what I actually want. Well, how do I find the reference angle? This is important. To find a reference angle, this is like a huge star. When you're dealing with trig now on this coordinate plane, you're going to have some ratios that are positive and some that are negative. The negative ones can lie to you, so it's really important use the positive ratio. Now I can use the sine, the cos, or the tan, just ignoring the negative for the moment. Doesn't matter. I'll use sine because it already is positive, so let's show you what I mean by that. I knew that sine was 7 over root 74. Using the positive, how do I find the angle? Just like I would have found the angle with grade 10 trig, I would have used the inverse or second sine. And I'll go to my calculator, make sure it's in the right mode. It's in degree mode, good. And I'm going to do second sine of 7 divided by root 74. Out comes 54.5 degrees. Remember, that's my reference angle. Okay. And now looking at the picture, just using common sense and the picture, the actual theta that I want, I know this is 54.5. 54.5. To figure out how much this must have been, well, it must be 180 take away the 54.5 degrees. And at that point, once I enter that in, or just use my numeracy skills, I end up with 125.5 degrees. Now just to show you, before we do the next example, of how these can kind of lie to you, let's say you went with this one. Now some lie, some tell the truth. And that's where you just don't want to bank it on, well, just whatever it is. If I use the tan one here, if I go second tan of 7 divided by negative 5, you get negative 54, which is not bad if you're on the ball to understand it. And if I do the cosine one of negative 5 divided by root 74, you actually get the right answer there. But again, you can't bank it on, well, I think it's going to be right. What I would recommend for both of those, if you use cosine, use the positive, you'll have the reference angle. Tan, use the reference angle. Or use the positive, you get the reference angle. Then you won't ever have to worry about, is it right? You'll get the reference angle all the time and just use the picture to find out the missing piece. So that's example 1. Example number 2. These examples get smaller as we go along, is the good news. So theta is an angle in standard position, good for it, with the terminal arm in quadrant 4. See, right away, if I read that first part of the question, I'd be like, I'm in quadrant 4 with my terminal arm. Thank you very much. My angle must be like that. There's what I'm talking about. And they gave me this information. They told me that tan theta equals -5/7. Okay, so that's a moment. How's that going to help me? Find the other two primary trig ratios. Okay, so part A, put it down here, like prime colors, red, blue, and yellow. The primary trig ratios are sine, cos, and tan. So they give me tan, they want sine, and they want cos. And then it wants us to find the angle, just like the last question. But this question gave us a little bit different information. It didn't give us a point, it gave us where we were, and it gave me one of the trig ratios. Well, one thing I could do this. I could write my reference angle, put an imaginary point in here again, go down here, make my right angle to the x-axis. I could use just my width and say, well, I know this is referencing the reference angle in a sense. This must be my opposite. This must be 5. This must be my adjacent, 7. Or I could just know that this is by definition x over or y over x. So -5 must be my y and 7 must be my x. And then once I have that, boom, I'm going to find the radius using x squared plus y squared equals r squared. So 7 positive squared, because that's my x, plus -5 squared, happens to be the same numbers as last time just by fluke. 49 plus 25, don't always get the same numbers, this is just coincidence. Radius is √74. Once I have the radius, boom, I know that cosine is y over r, -5 over √74, done. Cosine is x over r, 7 over √74, done. There's A. Just going to circle this data so I don't get lost. And part B, how do I find this actual angle? Well, I need to find the reference angle. How do I find the reference angle? I will use any one of the primary trig ratios, sine, cos, or tan. Let's say I wanted to use the tan one. I would do second tan of the +5/7. I'm not going to use the negative because the negative just tells me where I am. I'm not going to let that bully me around. So second tan of 5/7, 35.5. If I had used sine, same difference, I would have used the positive of 5 divided by √74. Would have got the same reference angle. And cosine, 7 divided by root. So there's no wrong choice. They're all going to give me the right reference angle. And then looking at the picture, just use my width. How big is that angle? That angle has to be, well, if I had gone all the way around, it would have been 360, but I'm backing up the reference angle. So it's going to be 360 minus 35.5. Should be able to do that in my head. Well, I'm not going to trust my head right now. It's been a long day. 36, okay, that gives me 324.5 degrees. All right, that's example 2. Example number 3. Weird question, but to be honest, this is a quick one. You just don't realize it yet. For each description, in which quadrant does the terminal arm of the angle theta lie? So in other words, is it quadrant 1, 2, 3, or 4? And then they give you this weird information. It's like, what does that even mean? Cosine theta is less than 0. Well, something less than 0 means negative. Sine theta is greater than 0. That means positive. And when they're asking you where things lie and positive and negative ratios, they're talking about the cast rule. So looking at that information, what quadrant has this information where cosine is negative and sine is positive? Well, if you have this already drawn out, you could just look at each quadrant and say, well, cosine is negative here and here, but out of those two choices, where is sine positive? Well, it must be quadrant 2. How I would personally do this, without that, I would use my cast rule. all suckers take cocaine. And I'd be like, okay, where is cosine negative? Well, what does the all mean? That means all are positive. Well, that's not true. What does the S mean? That means S is positive, cos and tan are negative. Oh yeah, so it could be here. That's one potential. T means tan is positive, cos and sine are negative. Oh, that's another possibility. It could be quadrants 2 and 3 right now. Cosine, the C means positive, so that's out because I want negative. And then same thing for sine. All suckers take cocaine. Where is sine positive? Well, it's definitely positive in the all positive quadrant, and it's definitely positive in the sine positive quadrant. So it's quadrants 1 and 2. Which quadrant makes both of these true? Quadrant number 2. Boom. That's it. That's the only logic behind that. Okay, next example is this next one. Right away, tan, negative ratio. Cosine, positive. So, where is tan negative? Well, it's not negative in the all quadrant. It's not negative in the tan positive quadrant. It's negative here and here. Where is cosine positive? In the all quadrant and in the cosine quadrant. Which quadrant meets both? Quadrant 4. Alrighty. Okay, and the last example, quickest of them all. Without using a calculator, state whether each ratio is negative or positive. So, cosine 152. Now, not using a calculator. Well, where's 152? 152 must be in quadrant 2. According to all suckers take cocaine, in this quadrant, sine is positive. Cosine of that angle has to be negative. Done. So if I go to a calculator right now and type in cosine of 152, I'll get a negative number. Tan of 120. Well, draw 120. 120 is also in quadrant 2. Yippee. So in quadrant 2, all suckers take cocaine. Is tan going to spit out a positive or negative in quadrant 2? Well, that means sine is positive. Tan has to be negative. And the last one, 300. 300 is in quadrant 4. All suckers take cocaine. Sine, positive or negative in quadrant C? Well, C is positive, sine, cos, negative. These happen to all be negative. That's just fluke. So that's an example of the cast rule through and through. All right, we'll leave it at that. You have a good day, and we'll talk to you later.